We've seen in the E2 reaction how it's important to notice whether your leaving group and beta hydrogen are anti or not in the case of cyclic alkyl halides. Okay, and then we have to look at chairs and that kind of thing. Turns out in acyclic halides, we also have to pay attention to this. So let's draw up a nice simple molecule. 2-bromobutane, and if we were to treat this with a base, just use our good friend sodium hydroxide again, you'd say, we have a strong base, we have a secondary halide, we have beta hydrogens. This is going to do an E2 reaction. And furthermore, I've chosen this carbon as the beta carbon because we're going to follow the Zaitsev rule. We're not going to form the less highly substituted alkene. We're going to make the more highly substituted alkene, and you very well may draw this as your product, or you could just, as likely, propose this is your product. Now notice these are two different products. They have a different geometry for the alkene. This is the trans alkene, or maybe more formally the E alkene, and here is the cis alkene, or the Z alkene. So which is it? Because the fact is, it's not just a random mixture. There is a preference in this reaction, and it all comes back to the fact that our beta hydrogens have to be anti to our leaving group. So let's draw a more specific picture of our molecule. There's our bromine. We'll define our stereocenter. And there are our beta hydrogens. So to do this, we need to look at Newman projections to see the relationship between our halide and our beta hydrogens. So here is one Newman projection. Looks a little clumsy, doesn't it? So we'll look with our eye down that bond, and on the front carbon, we'll have this put in our CH3. And looking back to our back carbon, the methyl group will be up. A hydrogen there, which is a nice staggered conformation, low energy conformation. And you'll notice we have our halide and a beta hydrogen are anti to each other, so this looks good. Well, there is another conformation that we could draw of this structure, another Newman projection, another staggered Newman projection. What we're going to do is we're going to rotate this hydrogen 120 degrees around on the back carbon, and of course everything else is going to move too. Our front carbon stays the same. And so that hydrogen moves. This particular, our former beta hydrogen, moves up to the top, and our methyl group rotates to the lower right. And now again we see, that's not a problem because our leaving group and a beta hydrogen are still anti. So these are both, anti. These are both valid potential conformations. However, these conformations are not identical in energy. If you notice, in the bottom case, to get our beta hydrogen and our leaving group anti, we had to put these two methyl groups next to each other, and this is a gauche interaction. That is a repulsion. That makes this a the lower conformation, a higher energy conformation. That means our top conformation is favored. It's energetically favored. Now, so if this top one is favored, and if we do the E2 on the top one, what we'll find is the two methyl groups are going to be anti in the product. Well, which gives us an anti-methyl groups in the product? It's the trans conformation. Trans configuration. Easy to cross up the lingo. Okay. So this particular Newman projection will give us exclusively the trans isomer. The bottom case, if we were to do this elimination, the two methyl groups would be on the same side of the alkene, and that would give us the cis product. Well, energetically, we favor, in part because of this gauche interaction in the lower Newman projection, we're going to favor formation of the trans product. So the conformational stability of the different conformations of our starting material actually have an impact on what the stereochemical identity of our products are. So again, lots of layers when you start getting into the nitty-gritty of having your leaving group and your beta hydrogen requiring an anti-relationship.